with the properties of eigenvalue and the Clay-Hamilton theorem, only the statement, not the proof, as per GGSIPU syllabus. So the first property is the eigenvalue of a square matrix. We will always take a square matrix A and its transpose are always same. See, how to find an eigenvalue? We know that A minus lambda I determinant. This is the way we find it. So what I do is that I know that if I take a matrix B, take its transpose, and then I take the determinant, this is going to be same as the determinant of the original matrix. This I know from the properties of determinant. So what I do is that let B be equal to A minus lambda I. Now what I do is that I take the transpose of B. I take the transpose of B. So what I'll get is that A minus lambda I whole transpose. This will give me A transpose minus lambda. I transpose is I itself. I transpose is just I itself. Since now what I do is that I take the determinant of this B transpose. So what I do is that B transpose, I take the determinant. Now what I get is that this will be A transpose minus lambda I, then determinant, which is will be same as, by this property, this will be same as your B determinant. Now that is nothing but A minus lambda I. So whatever eigenvalue I'll get for this, I'll get the same eigenvalue for its transpose. Next property, I mean to say second property. Second property is that if lambda is an eigenvalue, eigenvalue of a non-singular, I mean this has to be non-singular, this line is important, non-singular matrix A, then 1 upon lambda is eigenvalue, sorry, is eigenvalue of A inverse. See, in order that A inverse exists, A must be non-singular. I have told you, that is, the determinant of A should be non-zero. Then only A inverse will exist. Then A inverse exists. Otherwise, it does not. Therefore, I need this to be non-singular. Now let's come. Ax equal to lambda x by the definition. I pre-multiply with A inverse. Aax is equal to lambda is a constant. I can keep it out this way. A inverse, we know from this definition, A inverse A is equal to identity A inverse. From this concept, I can write it identity into x is equal to lambda A inverse x. Now what will happen is that I into x will give me just x only, because it's an identity matrix, lambda A inverse x. Now just take 1 upon lambda x is equal to A inverse x. This implies A inverse x is 1 upon lambda x. So the eigenvalue, eigenvalue of A inverse is 1 upon lambda. Now the third property is that if A is n cross n, of course this is a square matrix, has eigenvalues, lambda 1, lambda 2, up to so and so forth, lambda n. Because this is an n cross n matrix, I'll have till lambda n. Then A to the power of m, this is also n cross n, will have eigenvalues of the form lambda 1 to the power of m, lambda 2 to the power of m, and so forth, lambda n to the power of m. Let me take an example. Let me take ax. Let me prove it rather. Lambda 1x, say, for the first one. I'm doing it I will be doing it for a cube, and then that will hold for a n also. A to the power of m. Wait. Now see, I'll do it for this. See, I multiply both sides by a. Pre-multiply. This is pre-multiplied. Lambda 1 ax. Now this will become a square x. Now see, ax is lambda 1 x. What I'll do is this lambda 1, put lambda 1 x here. Now this will become lambda 1 square x. Now again I'll do for a square x. Now lambda 1 square ax, and again I'll use that ax is equal to lambda 1 x, and then I'll get lambda 1 square lambda 1 x, and this is going to become lambda 1 cube x. So now this is a cube x is equal to lambda 1 cube x. Similarly, if I carry on with this and now I write amx, this will become lambda 1 mx. Similarly for other eigenvalues. Similarly for other eigenvalues. That is for lambda 2 and up to lambda n. Similar process. Now we will see the next property. I think it is the fourth property. Yeah, fourth property. Fourth property is, as I've already told you, the trace of A is sum of the sum of the eigenvalues, that is lambda 1 plus lambda 2 plus up to plus n, and this is equal to summation I equal to 1 to n. That is the sum of the elements on the principal diagonal. Sum of the elements on the principal diagonal. On the principal diagonal. You can see my earlier videos. What did I mean by principal diagonal? Principal diagonal. Now, the fifth property, the product of the eigenvalues. Now, determinant of A is nothing but lambda 1 into lambda 2 into lambda n. You are multiplying all of these. And this is nothing but product of eigenvalues, and this is product of the eigenvalues. Now, if the fifth property is if lambda 1, lambda 2 up to lambda n are eigenvalues of A, then Ka has eigenvalue uh, of the form k lambda 1, k lambda 2 up to so and so forth k lambda n. I'll do it for lambda 1, and you can do it for the rest. Now see, what is the thing? X is equal to lambda 1x. Let me do it for lambda 1. Now you see, multiply both sides by k. Kax is lambda 1 k. Wait a minute. Let me write it in the. We are writing in the pre now. Let me write it in the pre. K lambda x. Now you see, Ka is k lambda x. Therefore, Ka has eigenvalue k lambda 1, and so on and so on and so on. Now we will write down, we'll do one more property before coming to the Clay-Hamilton theorem, that is We have, suppose I have a matrix. Suppose this is, I think, property number. Wait a minute. This is property number 6. Yes, we are doing the sixth one. We are doing the sixth one. That is, if A A is any matrix, A is a n cross n matrix, then then P inverse AP has the same eigenvalue, has the same eigenvalue. This I want to say, show. So let me P inverse AP minus lambda I determinant is equal to, see, I can be written as P, where P is invertible matrix. Otherwise, I will not get P inverse. Invertible matrix. This is very, very important, that P must be invertible. P inverse P. I can be written in this manner. So what I do is that I write here P inverse AP minus P minus lambda I, and again I multiply with an I, doesn't matter. Two identities will give me the same thing. So what I do is that P inverse AP minus lambda I P inverse P. Now what I do is that I write like this: P inverse AP minus P inverse. In the middle I put lambda I and I put this P here. No issue, I can do it. This is just a simple scalar multiplication. Now I do is I take P inverse common here. I take A minus lambda I here and I take a P here. Now I told you the property of determinants. A, B determinant is A determinant, B determinant, and A, B, C determinant is A determinant, B determinant, C determinant. Now see one thing. This thing here we can, this is like A, this is like B, and this is like C. So P determinant, then A minus lambda I determinant, and P determinant. Now I told you this A determinant, B determinant can be written as A, B determinant. Now this is A determinant, B determinant. I can write it P inverse P determinant, and this is A minus lambda I determinant. Now P inverse P is nothing but I, as I told you. I determinant into A minus lambda I determinant, and I determinant is 1. So this is A minus lambda I. So what I proved is that I took this and that I proved this. So whatever eigenvalue this has, so A minus lambda I has same eigenvalue as P inverse AP minus lambda I. This is the sixth proof. Now let us see the seventh proof. Seventh proof, if lambda is an eigenvalue, eigenvalue of an orthogonal matrix, then 1 upon lambda is also an eigenvalue of A. Earlier I told you in the earlier derivation that if lambda is an eigenvalue of A, then 1 upon lambda is an eigenvalue of A inverse. But here, since this is an orthogonal matrix, the moment I see this word, this should come in my mind. A transpose A is equal to identity is equal to A transpose for orthogonality property. Now I want to show that the lambda is an eigenvalue of an orthogonal matrix, then 1 upon lambda is also an eigenvalue of this matrix, of the same matrix A. You do one thing. You take, now from here A transpose A is I, right? So A transpose is equal to A inverse. This comes out. Now you see one thing. You take AX is equal to lambda x. You multiply A inverse both sides. Lambda A inverse x. Now see one thing. Here. Now A inverse is identity. Identity into x is lambda A inverse x. Now you can see that A inverse here is A transpose. So x is equal to lambda A transpose x. Right? Okay. Now, A transpose, see, let me rewrite it like this. A transpose x, lambda is equal to x. I'm just changing the way of writing. Now, from here, A transpose x is 1 upon lambda x, right? And the first property that we did is that that A transpose x has the same, this property I'm talking about. I'm talking about the first property, that is this property, that if the eigenvalues, I'm talking about this property. Wait a minute. Yes, this property I'm talking about. Wait a minute. Yes, I'm talking about this property. They have the same eigenvalues, A transpose and A. So this will, since I have to write here, since the eigenvalues, now you see A transpose X has the same eigenvalues. Therefore, A transpose and A have the same eigenvalues, since have the same eigenvalues. So Ax is equal to 1 upon lambda x. This is the reason. Now one more important fact that we need to see. This is, I think, property number 7 and 8. We have property number 8 now. We have property number 8. That is, if lambda is an eigenvalue of A, that is an n cross n matrix undoubtedly, then A plus Ki, where I is the identity matrix and K is a scalar, has eigenvalue lambda plus K. That is what I have to prove. Let me prove. A plus Ki minus lambda I. Let me start with this way. Wait. Let me start this way. A minus lambda I is equal to 0. This will give me the eigenvalues of A. What I do here is that I add Ki and subtract Ki. It hardly matters. So subtract Ki. Now I take it in this manner. This is A plus Ki minus K plus lambda I equal to 0. This behaves like B, and let us say this behaves like some lambda dash. So this has the same eigenvalue. Let B be equal to A plus Ki, and let lambda dash be equal to K plus lambda. So now it will look like B minus lambda dash I equal to 0. So lambda dash is an eigenvalue of B, that is, lambda dash is what? K plus lambda is an eigenvalue of what is B? B is A plus Ki. Now two more points to note. Suppose this is, I think, property number This is 8 and 9. Now doing the property number 9. Let me do the property number 9. That is, if lambda is an eigenvalue of A, then A square plus A will have eigenvalue of this form, eigenvalue of the form lambda square plus lambda. This is the thing. And 10th, which is very, very important, you should remember, if lambda is eigenvalue of A and suppose mu, this is to be written like this. See how to write this. This is a Greek alphabet. How to write this? You write U in this manner and call it mu. This is a Greek alphabet. Mu is an eigenvalue of B, eigenvalue of B, then listen, this is very important. A plus B will not have eigenvalue, just a minute, let me write it clearly. Have eigenvalue of the form lambda plus mu. Listen, we will not have in this manner. Now let's come down to the Cayley-Hamilton theorem. Let us write Cayley-Hamilton theorem. Now this theorem says that you only have the statement as per GGSIPU University, no proof and nothing. Every square matrix satisfies its characteristic equation. Suppose A is an n cross n matrix, then of course you will have of this form. Here the characteristic equation will be of the form a n lambda to the power of n plus a n minus 1 lambda to the power of n minus 1. This is n. Let me write it clearly. n minus 1 up to so and so forth. A2 lambda square, A1 lambda plus A naught equal to 0. Then this equation will be satisfied by A. That means I mean to say, if you replace lambda by A. So what will happen is that, wait a minute, let me write it little down. You will have a to the power of n plus a n minus 1, a to the power of n minus 1 plus so and so forth, a to the power of 2 plus a1 lamb a. Now you will have to write an identity because a is of that form. This will be 0. This was what is about Cayley-Hamilton theorem. Let me do questions on this and then you will be able to understand what I mean by that. Let me take the easiest one. I took a matrix, I hope you remember in my earlier video, I took a matrix A equal to 0, 2, 2, 0. I found out the characteristic equation as lambda square 4 equal to 0. Now this is my characteristic equation, characteristic equation or latent equation, easier way to write equation. Now see, what I'll do is that this a square minus 4i, I will show this is 0. See, what I'll do is that 0, 2, 2, 0. Again write 0, 2, 0, 2 minus 4 into 1, 0, 0, 1 because of the 2 cross 2. Now what I'll do is that, now multiply this with this. Sorry, I made a mistake while writing this. Just a minute. This 2. This is 2 0. 0 2. So I'll get is 0. I'll get a 4 here. Now this with this, I'll get a 0. I'll do this with this, I'll get a 0. And with this, I'll get a 4. And this is multiply 4 0 0 4. I know I told you how to subtract matrices. This will become 0 0 0 0. So I got a null matrix and the Clay-Hamilton theorem is satisfied. So Cayley-Hamilton theorem, Cayley-Hamilton theorem is satisfied. Is satisfied. Wait. Is satisfied. Satisfied. Okay, now we will take another example and then we will do this with a 3 cross 3. I did with a 2 cross 2. Now we will do with a 3 cross 3. Let me take a matrix A question. Let me take a matrix A and then let me do this. See what I do. I take a matrix 1, 2, 3, 2, minus 1, 4, and 3, minus 1, minus 1. I'm giving you the characteristic equation directly, though you need to find, see, trace. I think I found it in the earlier example. Yes, I have found it in the earlier example. Yes, I remember. I found trace as minus 1. Then I found the determinant as 40. Determinant of, this is, sorry, this is trace of, sorry, this is the trace A. I found it in the earlier example, so I'm not doing it again here. Trace A I found out to be minus 1. And determinant A I found out to be 40. Then I found out A11, I think it was minus 3. Then A22 was minus 10. And A33 was minus 5. So using this equation, lambda square minus trace A, sorry, this is lambda cube. Lambda square plus A11, A22 plus A33, lambda minus determinant A. I found out the characteristic equation that came out to be plus lambda square minus 18 lambda minus 40. This was the characteristic equation. Now I will verify the Cayley-Hamilton theorem. What I'll do is that I'll put a cube here. I'll do a square minus 18a minus 40i. I will not write a 0 here directly. I have to prove this. So let me rub it. Now I have to find a cube. I have to find a cube. Wait a minute. First I have to find a square. That will make me things easier for me. A into a. Just write this matrix 2 times. And I have already told you how to multiply. 1, 2, 3, 2, minus 1, 4, and then 3, 1, minus 1, and then 1, 2, 3, 2, minus 1, 4, 3, 1, minus 1. I have already given you how to multiply two matrices. I'm just giving you the answer directly now. I'm not doing the multiplication here. That is your homework. 14, 3, 8, 12, 9, minus 2, and then 2, 4, 14. This is a square. Now you need to find a cube. A cube is a square into a square into a. Now you have 14, 3, 8. Then you have 12, 9, minus 2. You have 2, 4, 14. 2, 4, 14. And then you have 1, 2, 3. 2 minus 1, 4. 3, 1, minus 1. You will get, I am not doing the multiplication, you will give me the straight away the answer. You will get 44, 33, 46, and then you will get 24, you will get 13, you will get 74, and you will get 52, you will get 14, you will get 8. Now, You will put these values of a cube, a and everything. Wait, you will have to put the values here. You have to put the values in this equation to show that this is equal to 0. Now I'll start putting the values. Now see, a cube. Let me write down the equation. You have this a cube plus a square minus 18a minus 40i. Now this becomes, what is a cube? I just found out what is a cube. A cube was 44, 33, 46. Then you had your 24. Then you had your 13. Then you had your 74. Then you had your 52. Then you had your 14. And then you had your 8 plus, let me write it little clearly, this one. Wait. This one has to be like this. Now a square you found out to be 14, 3, 8, 12, 9, minus 2. Then you have 2, 4, 14. And then you had 18 minus 18. The matrix, the original matrix, 1, 2, 3. 2 minus 1, 4. And then you have 3, 1, minus 1. And then you have minus 40 into the identity matrix. The identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Now you will do the component wide addition. How you add matrices. Now what you will do is that, see, you will get 44 plus 14, 18 minus 18, minus 40. This is the way you will write. Then 33 plus 3 minus 36 plus minus 0. Then you have 46, then 8, and 18 threes is 54 minus 54 minus 0. This is the first row done. Then you will have 24 from here plus 12 from here. 18 twos are 36 minus 36 minus 0. Then you have 13 plus 9 plus 18 minus 40. Then you have 74 minus 2. And then you have 18 fours are 4 is a 32, 72 minus 72. And then minus 0. The last is 52 plus 2. 18 threes are 54 minus 54 plus 0. Then you have your 14 plus 4 minus 18 plus 0. Then you have 8 plus 14 plus 18 minus 40. So if you do the calculation, which you can of course do, you can add and subtract. What you will get is 0, 0, 0, 0, 0, 0 and 0, 0, 0. So Calais-Hamilton theorem, Calais-Hamilton theorem is verified. This is one type problem. I'll take another type problem right now. That is question. You have, suppose A, you have a matrix A of this form, and you need to find A matrix is of the form 1, 2, 2 minus 1. You need to find A inverse, and hence you need to find A to the power of 8. See the trick. I told you A inverse is nothing but take the determinant of this matrix. First you take the determinant. Wait, take the determinant first. Determinant is minus 1, minus 4, and that is minus 5. The determinant is this. Very simple. Now you have to find A inverse. So what you do, you can find that way also. This is determinant A. You can do this way also. Lambda square minus, what is the trace? Trace of this matrix? Trace of this matrix is 1 minus 1 is 0. 0 lambda plus determinant A minus 5 equal to 0. So lambda square minus 5 is equal to 0. This is your characteristic equation, your eigen equation. Eigen equation, you can also write that a latent equation, eigen equation, characteristic equation, latent equation. Let me write something new here today. Let me write latent equation. Mostly the people use the word characteristic equation. Mostly. In most books you will find they use the word characteristic equation. Now what you do is that, say, they have asked you to find A inverse. You will use this to find A inverse. How? A square minus 5i. First you will see A square minus 5 is what? Find A square. A square is what? 1, 2, 2 minus 1 into 1, 2, 2 minus 1, and then you have 5, 1, 0, 0, 1. Sorry, 0, 1. Now you will have 1, and then you will have this as 2, 1, 1, 0, 1, 2, 2s are 4, and 5, 1, 2s are 2, 2, 0. Again, you will get a 0 and you will get a 5, and from here you will get 5, 0, 0, 5, and hence 0, 0, 0, 0. Calais Hamilton is again satisfied. Calais Hamilton will always be satisfied in the characteristic equation. Let me write one note for you. Wait here. Calais Hamilton. Wait, let me write it clearly. Wait. Calais Hamilton will always be satisfied by the characteristic equation. Characteristic equation. Keep this thing always in your mind. Now we have seen that a square we have a square minus 5i equal to 0. Multiply a inverse on both sides to find a inverse. See, what I'll do is that a square a inverse minus 5i a inverse is equal to 0. So a to the power of 2 minus 1, bases are same, powers are to be added, minus 5a inverse equal to 0. So a is going to become, from here it is going to become 5a inverse. So a inverse is 1 upon 5, wait a minute, let me write it clearly, 1 upon 5 a. So this is equal to 1 upon 5, this is going to be 1, 2, 2 minus 1. This is a inverse. Now I have to find a to the power of 8. I have to find a to the power of 8. I already know lambda square minus 5i is equal to 0. So lambda square is 5i from the characteristic equation. Now what I do is that I take the square of this. So lambda square, this will become 4. This will become 25i. Now I'll take the square of this again. Square of this will become lambda 4 whole square is equal to 25 whole square into identity will give me identity only. This will become lambda 8 is equal to 625 identity. So a to the power of 8 will be 625 1001, and that is going to give me a to the power of 8 is going to give me 625 00625.